Hey, everybody.
Hi, Professor.
Hey,
Hey, Professor.
how's it going?
It's going. Another short weekend.
Even shorter this last one than the
Right?
previous one.
Yeah. And then spring break's going to feel like a 3-day weekend.
Yeah, it always does. Spring
Wait,
break is.
when does spring break start?
We still have about one more month, I think.
Oh,
So still a bit of time, but I think that's our next long weekend.
Fun. Yeah, we'll see.
All right, we're going to be using Matlab today, so if you want to start that up, I think now would be a good time. I posted a starter code on the Canvas site too, and so if you go to week 5 on our course outline, you'll see that there's a starter code for 2D diffusion. So we'll be working on that one today. There's more in it this time than just a bunch of comments, so there's actually some starter code in there.
Which one is it again?
It's called Matlab starter code for 2D diffusion with finite differences. So if you go to week 5, it should be the last file on the page.
5. Oh. Thank you.
Mm-hmm.
Professor, where's the starter code located?
So if you go to the Canvas site and then you go down to week 5, so from the home page you go down to the course outline, you click the link for week 5, then there's a link to the file at the bottom there.
Two weeks until midterm.
Yep. Mm-hmm.
He just wanted to remind you.
Thanks for the reminder. I'm aware of it.
Man, do I want to do MATLAB with Python?
You can do it. You can do it in Python. Except I'm not sure how to plot it in Python. That's the only thing I'm not sure. I'm sure there's a simple function out there, but I've just never used it before.
Well, last time I was looking up how to do the gradients in Python. Let's see. What type of plot is it?
It's I use it's basically a contour plot. So if you can look up how to do like 2D contour color contours, that's what it is.
Oh. Oh, there is one. It's called contour XY.
Yeah, that sounds promising.
Just curious, why would you rather use Python than MATLAB?
I'm more familiar with Python than MATLAB. MATLAB, I mostly just use it like if it's forced.
Yeah, Python's also free. It's that's another good thing. And Python's open. It's open. It's more open too. So a lot of more people, a lot of more like users develop for Python. And so like for a class like this, it's you know there's really no difference. But if you want to do something more niche and researchy, you're probably more likely to find something useful in Python than MATLAB.
Well, it's not just that, is that once school is over, since this is my last semester, I won't have access, or I might not have access to MATLAB.
That's true. That's
So,
true.
you know, why would I put all these resources into learning? I mean, I feel confident enough in MATLAB, but I would rather put that time into learning more Python.
Mhm. Yeah, I mean, a lot of engineering companies they don't mind spending the money for MATLAB because it is only $100, which is not that much in the world of engineering software. But Python, you're right, is always going to be free, and you can use it for personal projects too.
We're just gonna use MATLAB, or we're gonna do or use other notes as well.
We'll probably spend first like 15, 20 minutes just writing down notes because I want to talk about how to apply boundary conditions because it'll make the code will make a lot more sense when after we kind of explain what I'm going to do, and then from there on we'll probably use MATLAB for the rest of the class today.
Okay. Are you gonna write them out, or can we follow along on some notes that you posted?
Yeah, you can just follow along. But yeah, if writing it down helps you remember it better, then you can write it down too.
Okay.
Yeah, I'm basically going straight from lecture note 05 for the 2D diffusion notes. Yeah.
Thank you.
Is the starter code like a couple of different codes? Because I have one that was because it comes with a function, so it opens up separately, right?
It should just be one code. Let me try to download it. Let me see. Yeah, it should just be one MATLAB file. But there's you'll see there's actually some code written in it. So you'll see that there's 10 steps to it, and then steps 1, 9, and 10, and 8 should have code in it.
Okay.
If you're just joining, we're going to be using MATLAB today. We're basically going to implement a 2D diffusion code together. And so I posted a starter code for that on the Canvas site. And so if you go to week 5 from our course outline, you should see at the bottom of the page there is a link to download this. It's called MATLAB starter code for 2D diffusion with finite differences. So if you can open up MATLAB and open up that script, we probably won't use it until about 15, 20 minutes into the class, but if you have it open, then you'll be ready to go once we get there. Yep. So it's if you go to week 5 on the Canvas site, and then at the bottom of that page, there's a code, a MATLAB starter code for 2D diffusion with finite differences. Oh. I think usually the way that I merge it back is I just, let's see. Yeah, usually I have it separate actually, so I'm not sure. But I think if you go to your MATLAB window, let's see, live script, no. Yeah, I'm not sure because I usually have it in separate windows like that. But probably somewhere in the settings, you can drag it back. I think usually the way MATLAB works, a lot of it's kind of click and drag. So if you can kind of drag the window back into your main window, then that can work too. Yeah, but usually I work with it separate just so I can kind of separate both my terminal and my script. Okay, it's 5:30, so let's go ahead and get started today. All right, good evening, everyone. How's everyone doing?
Good.
Going okay.
Good. Tired? Yeah. It's definitely getting to that time this semester. So I feel like, you know, the middle of the semester is you know, one of the really tough parts. I mean, the finals obviously is the most difficult part, but this is where like midterms, homeworks, and, you know, extracurriculars, everything kind of happens at once during this time of semester. So this is, you know, definitely a very busy time. Yeah, engineering dream, that's for sure. Okay, so today the plan is to continue on with our lecture notes for 2D diffusion. And so if you weren't here at the very beginning of the class, we're going to be using Matlab today. So the plan for a lot of today is to kind of walk through the implementation of a 2D diffusion code together. And so I posted a starter code on the Canvas site for you to download. And so if you go to week 5 of our of the course outline of the Canvas site, at the bottom of the page there, you should see a link to download a script called Matlab starter code for 2D diffusion. Okay, and so we're probably not going to use it until maybe 15 or 20 minutes after the class starts, just because I want to, you know, talk about some things first. But if you can have that open by the time we get there, then you should be good to go to follow along, right? Of course, you know, I'll be showing my code on the Zoom call too. So if you want to follow along just from a blank script, that works as well too. But the starter code just has some comments and has just some actual code that's written to kind of, you know, just to get things started. Okay. All right. So before we begin, are there any questions I can answer either about the homework or anything that we covered last week? Our midterm's not for a couple more weeks, so I think I'll wait until next week to talk about it. But it's going to be an in-class or in Zoom midterm, so 75 minutes. No MATLAB on that exam. It's just, you know, deriving the equations. But, you know, we'll talk about it more next week. It'll be homeworks 1. So there's going to be one more homework. So after you guys are done with this homework, I'm going to give you guys one more just to give you practice with you know, with the convection stuff, which is what we're going to start on Wednesday. It'll be a shorter homework, so homework 3 will be short. So it'll cover, the midterm will cover homeworks 1, 2, and 3. Yeah. Okay. All right. So there's no more questions. Let's go ahead and get started. Right. And so what we were covering last week was diffusion equations in 2D. Oops. Okay. And so actually, you know, most of what we spent last week was not really talking about finite difference, but more just, you know, bookkeeping and keeping things organized, right? Because I think the most difficult thing about jumping from 1D to 2D is just kind of staying organized with everything, right? And so our 2D domain is given by something like this, right? So you can call it a waffle, you can call it tic-tac-toe, you can call it whatever you want, okay? And then what we're interested in this figure are all the nodes here. Okay. Right. The first thing that's going to be important for our equations is to assign a unique ID number to each of the nodes, right? And so if you remember from last week, you know, we assigned the node numbers to look like this. Right. And so each of those nodes there has a unique ID number, right? And that's going to help us when we're developing the equations, right? Because remember, when we apply finite differences to a differential equation, we should get, you know, a system of algebraic equations, right? And just with finite, and the way finite differences is formulated, we're going to have one equation per node here, okay? Okay. Right. And so the reason we use this ID scheme, so the fact that, you know, the reason we assign a unique number is to kind of help us build our system of equations, okay? And then right alongside this, just to kind of keep track of also where each of the nodes are physically located, we also kept track of their ij coordinates, okay? is a lot harder on the iPad than it is in real life, right? Okay. And so basically, in addition to the ID numbers here, we're going to identify them by, you know, where they're kind of their XY coordinates, but we call them IJ, right? And so this coordinate down here will be 1, 1, okay? And so this one in the corner right here, this would be 4, 1, right? Because it's the fourth node to the right, and then it's still on the first row. This one right here would be 4, 3, okay? And so on and so forth, okay? And so when you're writing when we're writing our 2D code right here, you know, we're going to use kind of both of these interpretations because they're going to help us, one, develop the equations, and two, put those equations into the right place into our, you know, into our large linear system. Okay. All right. So what I wanted to talk about today was specifically how do we write the equations and how do we write the code for assigning the boundary conditions. Okay. And so by boundary conditions, what I mean is, you know, we want to write the equations for all of those, you know, all of the nodes that I've circled in red right there, because we've already done the interior nodes. Right? Because for the interior nodes, the ones that I've circled in blue, we already have an equation which governs their behavior, right? And so what we need now is an equation that governs, you know, all of the boundary nodes. Okay? And which equation that we use for it is going to depend on what boundary condition that we actually have. All right, any questions on this? This is just kind of just a recap from last time. Okay. All right. And so just to kind of remind you, so, you know, when you start getting in multiple dimensions, the boundary conditions can start to be really complicated, right? But for this class, we're going to make one kind of very important assumption here, which is we're going to assume that all the boundary conditions on one side of our square, all of those are going to be the same, okay? And so we only have 4 boundary conditions that we need to worry about. Okay. And so we're going to have a boundary condition on the left face of our domain, a boundary condition on the bottom face, one on the right, and one up top, okay? Because in reality, you know, kind of like, I think we talked about it kind of as a parting thought, you know, you can have one boundary condition on this part of the side, but then you can have another boundary condition on this part, okay? And that's when things start to get pretty complicated. But just for now, we're going to assume that all the boundary conditions on one side are going to be the same. And just like we did in 1D, you know, we have 2 types of boundary conditions that we can specify. And so the first type, which is the simpler one, is our Dirichlet boundary condition. Okay. And so these are pretty easy because we just basically assign a value for our solution at those nodes. Okay. And so we basically say phi is equal to phi naught. Okay. Where phi naught here is our specified value. And so that's something that's going to be given to you, or something that you're going to manually specify. Okay. And so the other type of boundary condition is our Neumann boundary condition. Or remember, for this one, we assign a derivative. Okay. Okay. And so we're going to specify the derivative of our solution here, and that's going to be, you know, our specified value. Okay. So the Dirichlet will actually be pretty straightforward. So, you know, that's not going to really change much from how we did it in 1D. You know, the only wrinkle that we have to throw in here is we have to make sure that we're computing the right ID number. Okay. But there's going to be an additional wrinkle to the Neumann boundary condition. Whereas if you notice, you know, the derivative that I put here is with respect to n. Okay. And what I mean by that is that this derivative here is, you know, because we're in 2D, you know, we can have derivatives either in x or in y. And so the reason I put n right here is because this derivative has to be taken in the direction normal to the boundary face. Okay. And I'll show you what that means when we get there. right, any questions on this so far? Okay.
To mean normal to boundary face.
Yeah, normal to the boundary face. Yeah, let's do it. Let's do an example of the Dirichlet first, and then I'll show you how to do the Neumann one. Okay. All right. So to kind of give an example, let's let me draw our domain again. We'll give them all our numbers. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. And so just for the sake of this example, let's say that on this right face, so for these nodes right here, let's say that we're going to supply a Dirichlet boundary condition. Okay. And our Dirichlet boundary condition states that phi is going to be equal to 50. Okay. And so for all the nodes right there, we need to write an equation that says that their phi value or their solution has to be equal to 50. Okay. And so what we're going to do is we're going to write out all the ID numbers for that face. And so here you can see we have ID numbers 4, 8, 12, and 16. And then let's write out the equation that makes it so that their phi values are equal to 50. Okay. And so since we have 4 nodes here, we're going to have 4 equations, and then they're simply all just going to be, phi 4, phi 8, phi 12, phi 16. All those are going to be equal to 50. Okay. Right. So relatively simple, right? So it's not that bad, but this is for the case when we only have a 4x4 grid, right? But what happens if we kind of expanded this so that we had, let's say, 50 nodes on each grid, on each side? Okay. Then it becomes a little bit not feasible to write them out by hand. Okay.
Professor?
Yep.
Would this have 12 solutions?
This particular grid right here,
Yeah.
it would have 16, or I guess if you're not counting the corner,
Because
we'll get,
four corners are shared, right?
yeah, right. So we'll get to the corner nodes in a bit. So I guess you're right. So for this one, there are only 12 things that we would have equations for. Yeah. Mm-hmm. Okay. And so you can see here that we have kind of a unique problem that we didn't have in 1D, right? Because in 1D, if you remember kind of how we did this, together last week, it didn't matter how many nodes that we had in our 1D domain, right? We could either have 6 nodes or we could have 600. It didn't matter because there were only 2 boundary points, no matter how many grid points were in between. And so, in other words, the number of boundary points didn't depend on how many other nodes that we had in our domain, because we just had 1D, right? Because in 1D, no matter how much you break it up, there's always going to be 2 points on the end. In 2D, the number of boundary points, it depends on how many grid points that you have overall. Okay? Because in 2D, our boundary are no longer just discrete points. Our boundary is actually, a full-on line. And so, when we go to apply our boundary conditions, we can't really just write out the equations kind of one by one. And so what we need to do is we need to visit all of the boundary points. And so what the way that we're going to do this is we're going to do this with a loop. Because a loop is great for this, because a loop is great for, you know, visiting lots of different nodes in a mesh like this, right? And so if you think back to 1D, we used the loop once we did the case with 50 grid points, right? And so the loop basically helped us visit all those points in a very kind of efficient way. And so in 2D, we know we're going to do the same thing. So we're going to use a loop to visit all of those nodes, but we're going to do it, you know, just for those boundary nodes. Okay. All right. Any questions on this? Okay. All right. So I'm going to show you kind of what I call like the. Oh, was there a question? So I'm going to show you what I call like the anatomy of these kinds of loops. So all of the 2D loops kind of have the same structure, even the interior nodes, which we'll get to later. And let me show you what I mean. So let me write this loop here to assign Dirichlet boundary conditions on the right side of the domain. Okay, and we'll go through this again, you know, once we're writing the code in Matlab later. But let me show you just kind of the anatomy of this loop, because a lot of the loops here are very, very similar. Okay? All right, so the first thing that you're going to have is for, okay? And so that for kind of signals to Matlab that we're going to write a loop. Okay? Next, we need a loop variable. Right? And so I'm going to choose J for this loop variable here. Okay. And the reason I choose J is because we have a vertical face, right? And so as we're going from, you know, as you can imagine for the loop, we're going to start from the bottom and work our way to the top, okay? If we think back to the ij coordinates for each of those grid points, our J is advancing from, you know, 1 to 2 to 3 to 4, okay? So that's why I choose J for the loop variable. Ultimately, you know, what you choose for the loop variable is fairly, you know, it's up to you, but something, oh, go ahead.
I'm so sorry. So will we be writing into the array backwards? Like filling it in backwards, since because you know how like an array is read from like left to right and then from top to bottom.
Yep.
But on the grid is from left to right and then from bottom to top.
Yeah, you'll see. So it really depends on the ID numbers, and so this is why, you know, this is why I want you to kind of always remember the I and J coordinates, and so that, you know, when we loop over I and J, we compute the ID numbers correctly for it. But yeah, you'll see how it's implemented. In a sense, you know, it doesn't really matter the order in which we visit everything, as long as by the end, you know, all the equations are kind of set to what they should be. Yeah. Okay. And so that's the reason I'm looping over J, okay? And then this J is going to go from 1 to NY, okay? So NY, remember, that's the number of grid points that we have in the Y direction. Right, and that's going to be the end. So the first part here that I want you to pay attention to is the for loop. Okay? And this for loop loops over the appropriate this for loop is going to visit all of the appropriate nodes. Okay. And so in this case, since we want to visit all of the nodes on the right side of the domain, then we loop over J like this. Okay. And so that's kind of the first part of these kinds of loops. Okay. Okay. And so the next thing that's common to all of the loops that we're going to write is we need some code to compute the ID numbers. Okay. And let me do this in a different color, actually. Okay. And so this code computes all the relevant ID numbers. In this case, since we just have a Dirichlet boundary condition, you know, we're only just going to compute one ID number, but you'll see once we do Neumann boundary conditions and when we do the interior nodes, we're going to compute more than one ID, okay? But in this particular case, we're just going to compute one ID number, okay? And the way that we're going to compute it is we're going to use our ID equation, right? So if you remember our ID equation, the way if we take, given the coordinates of a node I and j, we can compute its ID number using this formula here. And so that's a general, ID equation there. So you plug in I and j, you get the ID number. And so let's use the same thing here. Okay. But instead of I, let's plug in something special here, okay? Because what's special about all of these nodes on the boundary right here? All of these nodes are on the very right side of the domain, okay? And so all of these nodes on the right, they all share the same I value. Okay? And so particular, the I value for all these nodes on the right are going to be nx. Okay? Right? And still, instead of I in our general equation, we're just going to plug in nx because we're visiting just the nodes on the right side of the domain. Okay? Right? So that kind of makes sense about why we write that ID number like that.
And Professor.
Yep.
This loop comes before the loop on your sample code.
So I'll show you where it fits in on the sample code a bit later, but this is just kind of just talking about it in general. Yeah. Okay. And so all the loops that we're going to write today, they're going to have this this aspect to it. Okay. And then the last thing that you're going to write is another block of code here, and this is going to be different depending on what where we are and what boundary condition we're applying. But this is going to be code to modify the left-hand side matrix and the right-hand side vector. Okay. And so in this case, since we're just doing a Dirichlet boundary condition, it's going to look like this. Okay. And so if you remember from our 1D code, when we apply Dirichlet boundary condition, we set the diagonal entry equal to 1. Okay. Yeah. N squiggly. Oh yeah, it's nx. Yeah, sorry. Yeah, there you go. Mm-hmm. N squiggly. All right. Okay. And so that's what this line of code is going to do. It's going to set the diagonal entry equal to 1. And remember, everything else is starting out at 0, so we don't need to set everything else. Okay. Okay. And then the other thing we do for the Dirichlet boundary condition is that on the right-hand side vector, we insert in what that Dirichlet value is. And so in this case, the Dirichlet value is 50, and so we're going to put 50 into the right-hand side vector. Mm-hmm. Okay.
Professor.
Yep.
Sorry. The left-hand side matrix, is that the one that's 4 by 4?
Yeah. In this case, it's going to be 16 by 16, or I guess 12 by 12. We'll say it's 16 by 16. So we're going to have basically one row and one column for every node in our mesh. Yeah. Okay. All right. So I wanted to kind of break this one apart kind of slowly because it's all the other loops are going to kind of follow the same format here. Yeah, my ID is the same as my underscore ID. I just ran out of space to write it in that small box. Yeah. Mm-hmm. Yeah, so all the other loops that we're going to write are going to be similar in structure to this. I mean, the red, the black, the red, and the blue portions, they might vary depending on what part of the code that we're in, but it's going to be the same idea. Okay. All right, any questions on any of this? Okay, so let's talk about Neumann conditions really quick. Okay, and so for the Neumann boundary conditions, remember I put the derivative in terms of in terms of n, right? And so our Neumann boundary condition look like this. Okay. And so what I'm saying is that the derivative of phi in the n direction, that's what we're going to specify. Okay. And so what is this n direction? Right. And so let me rewrite this in kind of a form that'll be more useful for us when we're writing code. Okay. Because normally when we have a derivative like this, we just replace it with a finite difference. Okay. And so let me write that finite difference approximation. And so when we're doing these Neumann boundary conditions, we're going to take the difference between the phi value that's on the interior or the inner node minus the phi at the boundary node divided by gamma. Okay. Okay. And so what does this mean? So what do I mean by inner and boundary? So let's go back to our grid here. And let me just focus on just the left boundary. And let me draw its immediate neighbors. So this is 2, 6, 10, 14. Okay. And so let's say that in our problem, we're going to supply a Neumann boundary condition on these nodes. Okay. And let's say that the Neumann boundary condition is going to be equal to 10. Okay. And so basically the derivative of the function at those nodes has to be equal to 10. Right. So then the way that we do this, because when we take derivatives in 2D, we can take it in either the x or the y direction, okay? But when we supply Neumann boundary conditions, we're going to take the derivative in the normal direction. Okay? And so for this vertical face right here, the normal direction is going to be perpendicular to that. Okay? And so all your derivatives should be in this direction here, right? That I've indicated with the arrows. Okay. And so let's write the boundary condition for node number 1 first. All right. And so let's go ahead and apply this equation up here. So the inner node that's next to node number 1 here is going to be node number 2, right? Because it's one node that's inner from the boundary. Okay. And so that's our equation for node number 1. Right, so now let's write out the equation for node number 5. And so the inner node for node number 5 is going to be phi 6. And then the boundary node, of course, is node number 5. Right, so now let's do the equation for node number 9. Okay. And so the inner node for that's going to be phi 10 minus phi 9 divided by delta. This will be equal to 10. Okay. And then you can write out the same one for node number 13 too, but I kind of ran out of space here. Okay. All right. So the key thing here when you're doing Neumann boundary conditions. Okay. And so the key point here is that you're going to need to get ID numbers for 2 different nodes. Okay. Okay. You're going to need the ID number of not only the boundary node, okay? And so I call that my ID because that's my ID number, okay? You also need the ID number for the interior node. Okay, and so I'll call this inner ID. All right. And then the formula that you use for that inner ID is going to depend on which boundary that you're on. Okay. And we're again, we're going to use our same formula here. So remember, ID is equal to j minus 1 times nx plus I. Okay. But we're going to plug in specific values for I and j depending on where we are on the grid. Okay. And so I'll show you how to write the ID number equation for my ID and inner ID for that left face for that Neumann boundary condition. Okay. All right. Any questions on this? Okay. Oh, question. Right. So inner ID, that's going to be the ID number of its interior neighbor. Right. So every boundary node is going to have a neighboring node that's going to be on the interior of the grid. Right. And so basically, it's in the direction if you're on the boundary and you walk towards the interior of the mesh. Yeah. Yeah. So it's kind of like node minus 1, but it's with the ID number system here, you have to be a little bit careful on how you specify that ID. Yeah. And so in this case, it is just a node plus 1. But if you're on the top boundary, right? So let's say that we're applying a boundary condition on node 14 here. The inner ID for this one is actually going to be node number 10. And so you really need to kind of refer back to this equation right here and plug in the appropriate values of I and j, depending on where you are in the grid. Okay. So actually, let me do that for just this for just the green nodes here. Okay. And so for the left boundary, everything on the left boundary there shares the same I number, right? So everything on the left boundary has I is equal to 1. Okay. Its interior neighbor is going to have I is equal to 2, right? Because it's just going to be 1 on the inside. Okay. And so the equations that you're going to write in the code, you're going to have my ID. Okay, so my ID is going to be j minus 1 times nx plus I normally, but in this case, we're just going to do add 1. Okay. And then your equation for inner ID is going to be the same thing, but instead of I is equal to 1, you're going to plug in I is equal to 2. And so when we write the loop to apply the Neumann boundary conditions, you'll see that there are going to be 2 lines of code that specify, these equations right here. Okay. All right. And so once we go over the starter code and once we write through that, you'll kind of see that in action. Okay. All right. One more point I want to make before we jump into the example and jump into the starter code is talking about the corner nodes. Okay. Because it can be a little bit confusing on, what we actually apply on the corners here. Because the corners are kind of the intersection between 2 different boundaries. And most of the time, we're going to apply different boundary conditions on those 2 boundaries. And so the question becomes, how do we deal with these corner nodes when they have 2 boundary conditions applied at the same time? Right. So the short answer to this is that it doesn't matter. It only half matters, right? And so the reason it doesn't really matter is because those corner nodes, they never participate in any of the finite difference equations. Okay. And so just as an example, let me kind of draw just a corner here. So then let's say this is corner 1. Okay. And let's say this is node number 5 and this is node number 6. Okay. And so this is kind of the bottom left of our domain. And so there's kind of more domain in this direction and more domain in that direction. Okay. All right. And so for nodes 2 and 5, we're going to apply boundary conditions here. Okay. And so those equations will be set. And then for node number 6, since it's an interior node, we're going to apply a finite difference formula there. Okay. And so the finite difference formula for 6, if you remember, uses this 5-point stencil that looks like that. Okay. Because only on the interior nodes do we need kind of the neighboring nodes and the Neumann boundary condition, but the Neumann boundary condition only goes interior. Okay. Looks like a shuriken. And so you can see here that, at the worst, let's say that we have Neumann boundary conditions on 2 and 5, then the stencils for those nodes would look something like this, right? Okay. And so you can see here that no matter what scheme that we pick, node number 1 never participates in any of these equations. Okay. And so node number 1 is kind of like, the sad, lonely guy that kind of sits in the corner, right? He just doesn't, no matter what, no one wants to participate with him when they do their finite difference stuff, okay? And so it's a little bit sad, but it's, kind of the reality of these finite difference schemes. And so for these corner nodes, it doesn't really matter what we do there. And so, when we write the code, you'll see that we do something on the corner nodes, but we're only just going to assign one of the boundary conditions. It doesn't matter which of the boundary conditions that you apply, as long as you pick one, then it'll be fine. Okay. But what you don't want to do is you don't want to apply 2 boundary conditions at once, on the corner nodes, okay? Which is really easy to do because they're at the corners, and so you might accidentally loop over both of them. Okay? And so when we write our code, we want to make sure that we don't loop over both of those at the same time. All right, any questions on this before we jump into the starter code? So that took quite a bit longer than I thought, but I hope that now that we've kind of explained the loops, then things are a little bit more clear. Okay, so let's go ahead and jump into the starter code now. So I'm gonna go ahead and share my screen. Oops, that's the answer. Okay, and so the starter code should look something like this. Okay, so if you open up the starter code, it should be just kind of mostly comments here, but with some code mixed in. Okay, all right. And so for this starter code and for this example, basically what we're going to be doing is we're going to be solving this problem right here. Okay, and so we're going to be solving the diffusion equation on this square domain. And we're going to apply these boundary conditions. So on the top and the right sides, we're going to have Neumann boundary conditions. So one of them is going to be 10. The other one's going to be 0. And then on the bottom and left faces, we're going to apply Dirichlet boundary conditions. So on the bottom, we're going to apply a Dirichlet boundary condition of 25. And on the left side, we're going to apply a Dirichlet boundary condition of 50. Okay. All right. And so for this example, we're going to use a finite difference grid with 4 nodes in each direction, and solve for the numerical solution to this equation, okay? And so this equation right here, we have partial squared phi, partial x squared, plus partial squared phi, partial y squared is equal to 3xy, right? And so we have basically just a simple diffusion equation in 2D because we have our second derivatives and we have just a modest source term, right? Okay. All right, any questions on the problem setup? Okay. All right. So let's start. First thing, let's go ahead and label all of the nodes in our grid. Okay. So since we just have 4 nodes, we can just kind of simply write this down. But once we start getting more and more, it gets to be a bit harder. And so with 4 nodes in each direction, we have our 16-point grid that we've kind of been working with in the class. All right. And then from this grid, we can go ahead and take this differential equation and then discretize it using finite differences. And so what we're going to do is we're going to take the x derivative and then discretize it using finite differences. Okay? And so that's what we get right here. And then we're going to take our y derivative and then discretize that into finite differences. And so that's what we get there. Okay. And all that's equal to 3xy. Right? And so if we, kind of simplify this, just to kind of make it a little bit easier to work with, then we end up with our finite difference equation. Right? And so this is what we were working with last time. And so we have, representation from all the 4 neighbors. So here we have I plus 1, so that's the right neighbor. I minus 1 is the left neighbor. J plus 1 is the top neighbor. J minus 1 is the bottom neighbor. And then we have itself, of course, with a -4 coefficient. And then on the right-hand side, we have our source term and then delta squared. Okay, so that delta squared comes from the finite difference, approximation. Okay, and so let's go ahead and open up the starter script, and then let's go ahead and start working on, working on the code here, right? And so remember, first thing that we always have to do when we write a code is to define all of our variables. And so remember, variables are what's going to store all our information. And so let's go ahead and put all this at the beginning just so that we can kind of work from it here. Okay. And so I already have some of variables here for you. And so I have, nx, which is the number of grid points in the x direction. And so here we have 4. Okay. And then we have ny, which is the number of nodes in the y direction. And so that's 4. Okay. And then we have the total number of nodes here, which is n tot. And that's going to be just the product in between nx and ny. Right? And so pretty simple stuff. All right, and so let's go ahead and write some more equations for this, or more variables, because we're going to need them. Okay. All right, first thing we need to write is we need to write the length of the domain in the x and y directions. Okay. And so we're going to need Lx and Ly. All right, and so you can see from this problem right here, Lx here is going to be 1.5. So let's go ahead and put this as 1.5. Okay. And then Ly is also going to be 1.5. And so, if you want to put units on this, this could be like 1.5 meters. Okay. All right. Okay. And so now that we have the, the number or the length of the domain, and the number of grid points in the x and y directions, next thing that we're going to need is the grid spacing in x and y directions. Right. And so in this case, it's going to be the same, but let's go ahead and write separate variables for it. Okay. And so let's go ahead and use the information that we have. Right. So we're going to have, first we're going to have dx, where dx here is going to be the grid spacing in the x direction. And so to get dx, all we're going to do is we're going to take the length of the domain in the x direction, which is Lx. Okay. And then we're going to divide it by the number of grid points in that direction minus 1. Okay. And then same thing for y. Okay. Right. And so remember, the reason we do minus 1 here is because, with 4 grid points, we have 3 spaces in between each of the nodes, right? And so that's why we do minus 1. And so from there, we'll have the grid spacing in the x and y directions. Okay. Any questions so far? So we've just kind of defined some variables that we needed from the problem. Okay. All right, so a couple more variables that we're going to need is we're going to need a variable for the left-hand side matrix and also the right-hand side vector. Okay, because remember, the way that we set up these finite difference equations, or the reason we go through all this finite difference stuff is so that we can take a differential equation, which in this case is a very complicated partial differential equation, and then we're going to transform that into a linear system of equations. Okay? And so we're going to take that differential equations and turn it into something like this, right? So AX equals B. And so in order to do this, we need to have kind of placeholders for the left-hand side matrix A, and also the right-hand side vector B. Okay. Right. Remember, so the standard that we use for this is we use the zeros command because we want to create something with all zeros first. Okay. Right. And then the size of this matrix is going to be n total by n total. Okay. And remember, the reason for that is we want one equation for each of these nodes in the grid. Okay. And so since we have 16 nodes, then we should have 16 equations and 16 unknowns. Okay? And so be careful, because with a square grid like this, it's very tempting to do this, right? And so let's if you do nx and ny, right? Because our grid here kind of looks like a matrix because it's a two-dimensional square, but resist that urge. So remember, your matrix here should be n total because remember the matrix represents the set of equations. And so we want one equation per node, and so that's why we have n total by n total. Okay, and then the right hand side vector here will be n total by 1. Okay, because those are going to be all the right hand side equations or right hand side values. Okay. Okay, so that's all the variables that we need for this problem. Now let's go ahead and start applying the equations. Okay. All right. So first thing, let's apply this finite difference equation right here. Okay. And so we're going to apply this at all of the interior nodes. Okay. Right. Because for the interior nodes, we can apply the 5-point stencil because each of the interior nodes here will have all of these neighbors, right? Because remember, the condition for using this equation is for all of these neighbors to exist. And so that's only true for the interior. So for the boundary nodes, it's missing at least one neighbor, and so we can't apply the same equation. And so for the boundary conditions, we're going to apply boundary condition there. Okay. All right. And so the first thing that we're going to need to do is we're going to need to write a loop. Okay. And what this loop is going to do is this loop needs to visit every single interior node in our grid. Okay. Okay. And so loops work great for this because it's, loops are great for visiting a bunch of nodes like this. Right? Okay. And so for something like this, actually, where we're kind of visiting nodes in kind of a 2D space, it would actually work really well here to write a nested for loop. Okay. Okay. So let me put this in parentheses here to just kind of emphasize it. Okay. Because remember, besides this representation for the grid right here, we also have the same representation with the I and j coordinates. And so if we write a nested for loop where one of the loops, let's say the outer loop loops over I, okay? And then the inner for loop will loop over j, okay? This will be kind of a very elegant way to loop over all of the interior nodes in our mesh, okay? Because we've already kind of, characterized them in terms of that. And so we don't want to loop over we don't want to write a loop over the ID numbers, right? Because for this case, it's pretty easy to see that we need to visit nodes 6, 7, 10, and 11 because those are all our interior nodes. But once this grid gets to be much higher than this, let's say it's a 50 by 50 grid, it's going to be much harder to identify what the ID numbers are for just the interior. Okay, and it starts to get complicated too because if you start counting from 1 through 16, the only ones that are on the interior here are 6 and 7 and 10 and 11. So if you look at kind of a number line between 1 and 16, it's kind of a bit hard to kind of pick out which ones are going to be interior from that. And so for something like this, I think it's better to write a nest for loop where one for loop loops over I and the other one loops over j. I'll check out the Discord afterwards. Okay. And so in this case, let's write our I loop here. Okay. And so in this case, we only want to loop over the interior nodes, okay? And so the loop that I'm going to write is going to look something like this. Right. And so you can see I'm only looping from 2 to nx minus 1, okay? Right? Because if you look at kind of the ij representations of this, right, we know that I is going to go from 1, okay, on the left-hand side to nx, which is on the right, okay? But we don't want to go from the total left-hand side to the right-hand side. And so we only want to go from the 1 on the interior to 1 right before it ends, okay? And so that's the reason why we loop from 2 to nx here, okay? And the same thing we're going to loop over for j. So for j, we're going to go from 2 to ny minus 1, okay? All right, so let me write a comment here. So loop bounds chosen to only loop over interior nodes, okay? Right, because if you did this all the way, so like say that you did 1 to nx, right? So that would be kind of the full sweep from left to right. Then you would visit kind of the boundary nodes and the interior, but we don't want to visit the boundary nodes because we'll deal with them later, okay? And so we're only going to loop from 2 to nx minus 1. Yeah, so 2 is, so in this case, 2 is the starting index, and then we're going to go visit each one, all the way up until right before the end. And so for such a small mesh like this, it's a little bit, it seems a little bit trivial because we're going to go 6, 7, and then 10, 11, and then we're done. But for a much bigger grid, say this is 50 by 50, there's going to be much more to this. Yeah. Okay. And so from here, now that we're looping over all of the interior nodes, from here, what we can do is we can start to write the code to make the proper modifications to the left-hand side matrix and the right-hand side. Well, in this case, just the left-hand side matrix. Okay. Okay. And so the first thing that we need to do, just like we talked about when we did our Dirichlet boundary condition loop, is we need to compute the ID numbers for all relevant nodes. Okay. And then once we do that, then we can move on to the next block of code where we're going to make modifications to the left-hand side matrix. Okay. And so in this case, we're just going to make modifications to the left-hand side matrix, but nothing to the right-hand side, because we're just going to basically concern ourselves with this part of the equation right here. Okay. Okay. And so first thing, let's go ahead and compute all of the ID numbers. And so if we look at the section of the nodes that are kind of highlighted in blue here, you can see that we need 5 ID numbers. Okay. And so we need an ID number for myself, which is the IJ node. Okay. Then we need the ID number for the right neighbor, then the ID number for the left neighbor, then the ID number for the top neighbor, then the ID number for the bottom neighbor. Okay. So let's go ahead and write out the codes for all these. Okay. So we're going to have a code for my ID, then code for left ID, then a code for right ID, then for top ID, then for bot ID. Okay. Right. So we need all of these guys because we need all of their ID numbers. Right. And so for these ones, remember, we're just going to plug in our formula. Okay. And so we're going to have j minus 1 times nx plus I. Okay. And so in this particular case, since we have both I and j in the loop, we can have I and j in these formulas here. Okay. Okay. And so now let's write the ID number for the left neighbor. Okay. And so the left neighbor, is going to have a very similar formula to my ID here, but instead of having just be plus I, we're going to do plus I minus 1. Okay. Right. Because remember, our left neighbor has the same ID number as that one, except the I is just minus 1. Okay. Right. And so same for the right neighbor. And so for the right neighbor, we're going to have the same equation as my ID, but instead of just I, we're going to plug in I plus 1. Okay. So actually, let me put parentheses here just to make it a little bit more clear. Okay. So these parentheses here are optional, but I'm doing it just to kind of highlight, how I got these equations. Okay. Okay, and so now let's write out the equation for top ID. And so top ID, we're going to use the same equation as my ID here. Okay. But instead of j, our top ID has j plus 1. Okay. And so we have j minus 1 plus 1. Okay. And so the minus 1 and plus 1 are going to cancel out. And so we just have j times nx plus I. Okay. And for the bottom ID, we're going to have j minus 2 plus I. Okay. All right. Any questions on how we computed these ID numbers here?
Yeah, why is the bottom one j minus 2 again?
Right. So because remember, we're all starting with this this is kind of the base equation for the ID number here. And so for just I comma j, which is what we have right here, this is how we compute the ID numbers. Okay? And so for the bottom ID, we're going to use the same I value, but instead of j, we're going to plug in j minus 1. And so this 2 right here is basically j minus 1 minus 1.
Oh, okay.
Yeah. Mm-hmm.
Thank you.
Okay. All right. And so now that we've computed all the ID numbers, we're ready to make the modifications to the left-hand side matrix. Okay. And so we need to make 5 modifications here because we need to make a modification for each of these different terms, okay? And for each of the different IDs. Okay. All right. So all of these lines are going to start the same. Okay. So they're going to all start with a my ID. Okay. Because we're modifying this matrix one row at a time. Okay. Because remember, what we're basically doing is we're inserting this equation here into our matrix. Okay. And we're doing it by the row. Okay. So we're basically modifying the row in the matrix that has to do with this equation right here. Oh, I'm sorry, not A. We have a left-hand side matrix. Okay. And so basically what we need to do now is we need to write out the coefficients for each of these different nodes. Okay. All right, so let's start with the right neighbor, okay? Because that's this term right here. And so for phi I plus 1 comma j, we know that this guy is our right neighbor. Okay, so we're going to have right ID. Okay. And then the coefficient in front of that term is going to be equal to 1. Okay. Then let's do the left neighbor. And so a at my ID comma left ID, okay, this is going to be equal to 1 right here. Okay. And so the same thing for the top and the bottom. Okay. And then finally we have my ID, which is the diagonal term. Okay. And since in this equation we have a minus 4 out in front, then we put a minus 4 into the left-hand side matrix. Okay. All right. And so what we've done basically now is we've implemented this equation, or at least this part of the equation right here, into our linear system. Okay. And so our left-hand side matrix has the appropriate coefficients, according to this equation right here. Okay. All right. And so remember, the reason I'm using my ID for the first slot here for all of these guys is because, that's just to make sure that all of these entries are going on the same row, right? Because remember, when we specify coordinates in the left-hand side matrix, we do it by row, comma, column. And so in this case, I just wanted to specify it for the rows, okay? And so that's why I had it just be all my ID, because all of these are going to the equation for this my ID equation here, okay? And then I changed the columns here according to which of the neighbors that we're modifying, okay? And so, we have my ID comma right ID for the right neighbor, my ID comma left ID for the left neighbor, my ID comma top ID for the top neighbor, and my ID comma bottom ID for the bottom neighbor, okay? And then my ID here is just going to be minus 4 for this guy right here, okay? All right, any questions on this? I know it's a lot of things to kind of keep track in your head. So, definitely, kind of just try to write down the code right now and, try to, look at this again and look at the homework and try to make sense of it later. But I know it's kind of a lot right now, especially with grids and matrices and equations and all that stuff. So it's a lot, I know. So that's why, I'm trying to go slow, but, at the same time, I know that it's something like this doesn't make sense until you actually go and do it. Okay. And so now that's one part of the equation here. And so now let's go ahead and apply the second part. Actually, let me check. Okay. And so the second part here is going to be our forcing function. And so that's going to take place just on the right-hand side vector. Okay. Okay. And so that's going to be section 3 right here. So section 3, we're going to apply the forcing function to all the nodes in the mesh. Okay. Okay. And so the key here is all the nodes. And so just like the same as we did up here, we're going to write for loops. For I and for j, because we need to visit every node in the grid. Okay. But since this equation right here, this equation, the forcing function doesn't really care if we're on the boundaries or not. We're gonna write the full loops for this. Okay. So this can go 1 to nx. Okay. And j is going to go from 1 to ny. And so just like the same as we did before, we're gonna have to compute the ID numbers. Okay. But in this case, since we're just applying the forcing function, we only need my ID. Okay. So we don't need the ID numbers for any of the neighbors because they're not going to factor into what I have highlighted there. Okay. And so my ID, we're going to use the same equation as before. And so it's just going to be j minus 1 times nx plus I. Okay. And so far, so good. All right. So the next thing that we need to compute, which is actually unique to this part of the equation right here, is we need to compute xi and yi. Okay. And what xi and yi are, those are the physical x and y coordinates for the ij node. Okay. Okay. All right, so we'll call this xi, and we'll call this yi right here. Okay. All right. And so for xi, the way that we're going to compute it is basically like this. So we're going to take the I coordinate. Okay. So remember, the I is kind of the count. You can almost think of it as like the counter coordinate in the x direction. Okay. We're going to do -1, and then we're going to multiply by dx. Okay. And for the y coordinate, we're going to do j minus 1 times dy. Okay. Right. And so these equations right here will basically get us the physical xy, assuming that our origin here, node number 1, has xy coordinates of 0, 0. Okay. Right. And so from these equations, hopefully it kind of makes sense why we did this, right? Because remember, dx is the grid spacing in the x direction. So it's the amount of space in between, say nodes 1 and 2 right here. Okay. And then by multiplying by I minus 1, what we get is kind of the where that node is in the horizontal direction, okay, in terms of the I coordinate. And then by multiplying by dx, then we get the kind of the physical coordinates of that node, okay. And so that's why we have I minus 1 times dx. Then for y, it's kind of the same thing. So for yi, we have j minus 1, which is the ij coordinate for the vertical direction, times dy, which is the spacing in the y direction. Okay. Okay. So any questions on that?
Does that make the 1, 1 location essentially the origin, where it'd be 0, 0?
Exactly. Right. Yeah. So we're assuming that the node number 1 right here with ij, if ij is equal to 1, 1, then we're assuming that the physical coordinates of that is going to be 0, 0. Yeah, the origin. Mm-hmm. Okay. And so now that we have xi and yi, we can just basically implement this equation right here. Okay. And so since this equation right here doesn't have any phis in it, right? So it doesn't have any phi ij, this equation right here is going to go into the right-hand side vector, okay? Okay. And so we're going to do right-hand side vector at my ID, okay? Because we want to modify this for the correct row, okay? And so then from here, we're just going to implement the equation. So we're going to have 3 times xi times yi times, we need to do the grid spacing squared. So you can either do times dx squared, or you can do times dx times dy, or you can do dy squared, okay? And so all of those are the same because dx and dy we assume are the same in this case, okay? All right, and so this line of code right here modifies the right-hand side vector for the forcing function or the source function for this node. Okay. And so that takes care of this right here, okay? And so all of the finite difference equations and all of the forcing functions or the source functions are taken care of. And so now what we need to do is we need to write the code to take care of the boundary conditions, okay? All right. I kind of had my terminology mixed up here, okay? So let's start with the left boundary, okay? And so for the left boundary, you can see that we have a Dirichlet boundary condition of 50, okay? And so I'm going to go ahead and write the same, loop that we had before, okay? Okay. And so remember, for the left boundary, we're just looping in I because we're just going in the vertical direction, right? And so there's no need to loop in J because, or loop in, I'm sorry. So for the left boundary, we're only looping in J because we're going vertically up, and there's no need to loop in I because there's no need to go horizontal. Normally, question is, I thought you had to put a period after the caret sign. And so for this case, since we're kind of, doing all of these are scalar operations here, you don't have to do a period in front, but you can if you want. All right, hang on for a second. I already fed the cat, so don't feed the cat again.
Okay.
Okay. Yeah. Okay. And so since we're looping from J is equal from 1 to ny, that's going to take us all the way up from the on the left boundary. Okay. All right. And so now let's write out the same sections of code that we have in these ones, but we're just going to do them for just the that y-axis. Okay. Okay. And so just like we did up there, first thing we need to do is compute all the relevant ID numbers. Okay. And so in this case, since we're just doing a Dirichlet boundary condition, so we're just going to have a formula for my ID. Okay. And so we're going to use the same equation here. So my ID is going to be equal to j minus 1 times nx, okay, plus I. Okay. But in this case, since we're on the left boundary, I is equal to 1, right? And so, we can't plug in I right here, so we need to plug in 1 right here. Okay. All right. All right, so then after we compute the ID numbers, then we have to modify the appropriate locations in the left-hand side matrix and the right-hand side vectors, okay? All right, and so for a Dirichlet boundary condition, we just have 2 modifications to make. All right, so the first modification is going to be on the left-hand side matrix. And so for the diagonal term, we're going to have this, okay? Right, and so that sets the diagonal term equal to 1. And then on the right-hand side vector, remember for a Dirichlet boundary condition, we set that equal to the, whatever that Dirichlet value is. So in this case, that Dirichlet value is 50. And so that's what we're going to implement right there, okay? Right, any questions on how we apply this Dirichlet boundary condition? So this is kind of like the real implementation of, what we kind of wrote out in our notes earlier.
Can you mention again why the relevant ID numbers you have +1 instead of I? That kind of like.
Yeah, sure. So remember, for in this loop right here, we're applying the boundary condition on the left boundary. And so it's basically all the nodes here. So actually, let me do it down here, make it a bit easier. Right. And so we're only going to concern ourselves with these nodes that I've highlighted, because that's where we're applying the boundary condition. And so one thing that all of these nodes have in common here is that their I coordinate is the same, right? Because we're not traveling horizontally at all, so we're just going vertically up. And so, you know, the I coordinates for everything on this boundary right here is 1. And so that's why I've replaced I by 1 in this equation. Yeah.
Okay.
Okay. All right, so I'm going to make one small modification here, and that has to do with the boundary, with the corner nodes, right? And so remember what I said earlier. So for the corner nodes, you know, we don't really care what they do most of the time, but we don't want to apply boundary conditions twice on the nodes, okay? Because what you can imagine here, so for sections 5, 6, and 7, we're going to write loops that, you know, that loop over the boundary nodes. And so, you know, we have the potential to visit these boundary nodes twice, okay? And so to prevent that from happening, what I'm going to do is I'm going to cut off this, you know, this loop a little bit early, okay? And so instead of looping from 1 to ny, which is the top here, I'm just going to go from 1 to, you know, 1 short of that. So we're going to go from 1 to ny minus 1, okay? Okay. All right. And so that's the left boundary. And so now let's go on to the next section here, where this is going to be the Neumann boundary condition on the top. Okay. And so we're basically going to be looping over these nodes here. Okay. All right. And so for this one, you know, we're going to write our loop to have the same anatomy as before, but instead of j, we're going to loop over I, right? Because for everything on the top right here, all of these have the same j coordinate, but they have different i's. Okay, so we're going to go from 1 to nx. Okay, right. And then same thing as before. So we're going to compute the relevant ID numbers. Okay, and so we're going to have my ID. Okay, and so my ID, we're going to have j minus 1 times nx plus I. Okay, but instead of j right here, we're just going to go ahead and plug in the value here. Okay. And so all of the nodes here on the top have a j value of ny. Okay. Oh, we need one more here. So since this is a Neumann boundary condition, remember we have to compute the inner ID as well. Okay.
Professor?
Yep.
The top line 79, that's ny minus 1, right?
Yes, ny minus 1. Mm-hmm. Okay. And so remember, when we do Neumann boundary conditions, we have to also get the ID number of its inner neighbor here. Okay. And so for this top boundary, its inner neighbor is going to be 1 below it. Okay. And so you can almost think of it as, you know, we're finding the ID number for its bottom neighbor. And so the way that we get the bottom neighbor is we take the j value from the previous one, and then we just subtract 1 from it, okay? And so that's why I have, you know, ny minus 2 here, because in our base equation, we have ny minus 1, but if we subtract another 1 from that, then we just get 2, okay? Okay. Then we're going to make the appropriate modifications to the left-hand side vector, left-hand side matrix and the right-hand side vector. Okay, so first we're going to do the diagonal term. Okay, so for a Neumann boundary condition, that's going to be minus 1. Okay, and then for the inner neighbor, we're going to have a 1 right there. Okay. Okay. And then, you know, for the right-hand side vector, we're going to have our Neumann value, where in this case, the Neumann value is 10. Okay. And then we're going to multiply that by dy. Okay. Because remember that dy comes as a result of the fact that we have a delta in the denominator here. Okay. Right. Okay, any questions on that? Okay. All right, so we are out of time. So unfortunately, I'm not going to get to finish section 6 and 7, but 6 and 7 is really just a repeat of sections 4 and 5 right here, except they have different values here. Okay. So actually, for just because this is very close to the homework anyway, and so why don't you guys go ahead and finish this up, for the homeworks, because you're going to need it, for the homework problems, and see if you can get the plot. Okay, because when you run the code, you should get something looks like this. Okay, and so this is for a grid with 50 grid points in each direction. Okay, and so let's go ahead and see if you can implement those last two loops in section 6 and 7, which you can kind of see right here, I guess, and see if you can get this this solution right here. Okay. Right. And so in order to get something smooth like this, you might have to change nx from 4 to 50. Okay. But if you can get this, then you've implemented the code correctly. Okay. All right. So thank you guys for tuning in today. Sorry I ran over a little bit. But when we come back on Wednesday, we're going to start the next section of the class, which is going to be on convection. Okay. So thank you guys for tuning in today. Hope you guys have a good evening, and I'll see you guys on Wednesday. Section 5, yep, you can see that.
Hello, Professor. Quick question. When are you going to upload today's lecture?
As soon as it finishes converting. So basically what I do is it takes about an hour to convert, and then I usually upload it again after that.
Okay, perfect.
Yeah.
Thank you, Professor.
Yeah, it'll be up before 8 o'clock today. Yep.
Got it. Okay. I was just following along, so I wasn't, working it out. I was just seeing what you were doing, but thank you.
Mm-hmm. Yep. Okay. Yeah, I'll check it out after class. Thanks, guys.